Okay.
So, Badri, if you want, you can switch on your camera if you want people to see your face. This is up to you.
Sure, I can do that. If I can get back to the window.
Sometimes it works, sometimes it doesn't work. But don't worry. If it doesn't work, it's fine.
Okay, can you see me?
Yes, we can see you now. Perfect.
Okay.
So Badri is. Watch out because my clock is going to tick now for 7 times. But in any case, so Badri is an old friend of mine. I met him at the Albert Einstein Institute back in 2005, I think. And he's I'm flattering all of the speakers, but it's because I really believe that he's a very smart guy and a very nice person, and it really pays off to listen to him. So go ahead, Badri.
Okay, thank you, Pau. So let's see if it pays off. So the goal of this talk is to try and convince you that LIGO really sees black holes. And this, I mean, it's not obvious initially, but hopefully it'll be clear by the end of this talk. So let's see, okay. So it's a very simple talk. So please interrupt and ask questions when I want. So there's very few slides. So Pau asked me to limit the number of slides, and I thought I would get it below 10 slides, but I didn't succeed. But it's only 15 slides, including the title and the table of contents, so it's not so many. But in the end, people have to ask questions, and I think otherwise you won't get that much from it. Okay, so let's start. So there's essentially two parts to the talk. The first is to do with this event called GW150914. This was the first binary black hole that was seen. And so the goal of the talk in that part will be very heuristic. So I'll just try to give an idea for why we believe that the things that you see there are to do with black holes. And the second part is actually this proof that I mentioned of how do we believe that these things we see are Kerr black holes. And that is to do with a different event. It is 190521. So which means that the event happened in 2019, in May. So that's the fifth month, on the 21st. So 21st of May, 2019. So that's almost exactly 2 years ago. And that's a very special event. So I'll talk about that, and I'll explain why I think that proves that the thing that we see is a black hole, or proof as far as we can in this field. Okay, so let's start, and again emphasize, please ask questions at any time during the talk. And Pau told me that I should expect a constantly interrupted talk, and I'm happy if that happens. Okay, so this is so by the way, I should say that Monica's done a great job so far, and that a lot of the things I want to talk about, she already mentioned them, so I think things are a bit easier for me. So she already showed you this a slide which had the same data that I'm showing here. So this is the data from the Ligo detector. So that is the Hanford detector. That is the thing on the left. By the way, can you see my mouse cursor?
Yes, we can.
Okay, excellent. So the panel on the left is to do with the Hanford detector. So that if you know the geography of the US, so that is on the northwestern side of the US, and Livingston is on the diagonally opposite side. So that is the Louisiana, so that the southeastern side. So they're separated very far from each other. So there is a certain light travel time between the two things. So which means that the signal from whatever the signal is, this capsule signal, will reach one detector before the other. And what is done here is that you take the data from one detector and you shift it in time so that the two things agree. That accounts for this light travel time between the two instruments. And the other thing that has been done is to flip the sign of one. So as it turns out that the two detectors, so they're L-shaped, but they have different opposite orientation, which means that in effect there is a negative sign between one detector and the other. So on the left panel is the data from the Hanford detector. And on the right, what has been done is to shift the Hanford detector and to invert it. And then you see that the data is aligned between the two detectors. And And yeah, so this says that the two detectors are seeing essentially the same signal. It just happens to be at different times. Um, these two are the bottom panels are not important. I'm just going to focus on the top left and the top right panel. So this is what LIGO saw back in 2015. So again, this number 150914 means that this was 2015. So this September, and the 14th of September. And the question then is, why do we believe this is a binary black hole system? And if you ever heard any talk by connected to LIGO, you'll have seen quite complicated data analysis methods, and you'll have there's a lot of complications. But as first is you also want to know sort of a rough idea for why one believes this is really a black hole system without doing very many complicated things. And in this case, you can already get an idea for that by doing something without any computers. So what you can do is you can simply go to the LIGO website. You can download these two images. And what you can do for what I'm going to talk about in the next 3 or 4 slides is print this on a sheet of paper, a big sheet of paper, and get a pencil and a ruler and maybe a calculator. And then I think the rest you should be able to do without any complicated computing, without any complicated statistics, and so on. And the reason you can do this is that the signal is clearly visible by eye here in these panels. This is not normally the case. So normally what our data analysis partners are meant to do is to extract these signals when they're buried deep in the noise, right? I mean, after all, you don't need to have hundreds of people with millions of dollars detect something if you can just see it by eye by looking at this data here. So this is a very unusual event. So it was very loud, which means that you could really see it like this. And this also means that you can actually extract information about the system just based on these pictures. So again, I'm not going to go into details of gravitational waves and linearized gravity and things like that. I'm just going to use very, very simple results from GR, which I hope that you've seen before at some point. But if people want some of the details for that, I guess we can discuss that separately. But it's not going to be much. It's going to be just one equation that I need from GR. And that is the following. So before we do that, let me just look at the features of the signal. So it's easy to say signal frequency of this event increases from about 35 to about 150 hertz over about 8 cycles. So what I mean by that is the following. So you look at these oscillations that you see here, and you try to find sort of the frequency of this oscillation, which means that, for example, I just look at the x-axis, this line here, and I look at the zero crossings of the data that you find here. As you go later, you find that the crossings are closer to each other, which means the frequency is increasing, and you see that the amplitude is also increasing. Right? So it's an event which has an increasing frequency and an increasing amplitude. As you go near this peak of the signal, you find that the frequency gets to a maximum, and the very last part, the frequency goes to essentially a constant. And this you can deduce simply by looking, just as I said, printing out this on a big sheet of paper and looking at the zero crossings of this data here, right? And just measuring the time between successive zero crossings. Right, and then you can do the same thing for the Livingston-Hanford detector, and as this shows, I mean, the two things are consistent. So this picture of a signal which has an increasing pitch and increasing amplitude, so that is consistent, right? So then you ask yourself, well, what could possibly produce a signal which has an increasing frequency and an increasing amplitude? And so that is one thing that you have to accept here. So one hypothesis here is that this is a binary merger. So it is two objects orbiting each other and then merging at some point. I suppose it's an interesting to sort of think of what other models are possible to explain such a signal. So I suppose you could imagine a star that is collapsing, then preserving angular momentum, so it's spinning faster and faster. I suppose that is possible, but I think it's hard to make it work out. But at least one thing that we can assume here is that let's just, for the moment, think that this is a merger of two binary objects, okay? Of two objects in the binary. And then, which means that the orbital frequency of the system must be half of the frequency that is shown here. Why? Because roughly of equal mass systems, then the two objects here, or you switch them around, that is roughly the same situation. So then there's a symmetry in the problem. So that means that the orbital frequency is expected to be half of the frequency that you see in the signal. So that means that the maximum frequency of the binary system is 75 hertz. And again, this is quite rapid. I mean, think of the Earth going around the sun. That takes 1 year. So it goes 75 times in 1 second at the peak in this case.
I'm sorry, can I ask a question?
Yeah, sure, go ahead.
So the frequency goes to infinity in t equals t c. So is this derived from a linearized model?
So I'll come to that. I've not come to that yet,
Oh,
right? So
okay.
at the moment, I just want you to look at the signal here, and just to understand that you can measure the frequency just by looking at the signal visually, right? So you can.
Oh, okay. I'm sorry. Please
That
continue.
is the
Thank you.
first point, of course, and we'll come to that in a second. But at the moment, I just wanted you to sort of keep in mind that if this is a binary system, and if you believe that oscillations are produced by a binary system, that means that the orbital frequency should be half of the signal that you see in the signal, or frequency you see in the signal. And then we come to exactly the point that you just said, which is, well, what does GR tell us? So GR tells us that if I have two objects orbiting each other, at least to leading order, the rate of change of frequency of the of the orbit must be given by this equation here. So if you've never seen this before, this is coming from two assumptions here. This is coming from well, there's different to derive it. So in the simplest way, you can see this is coming from the quadrupole formula. So that tells you that if I have this binary system, so from that I can calculate this quadrupole moment. And then from the quadrupole formula, you know the derivative of the rate of change of the quadrupole moment, that determines in effect the rate at which energy is lost from the system. Okay. And that, yeah.
I'm sorry, can I ask something on this formula? Is
Sure.
this derived under the assumption of, how do you say it? Are you using post-Newtonian approximation, post-Minkowskian?
It's post-Newtonian, yes, in this case.
Okay. So you assume that the initial velocities are small enough so it can be so that this formula is valid, right?
So yeah, so it's going to be, well, I'll mention that. So this is not expected to be valid indefinitely, right? So of course, for this you need to have two objects, and if the two objects are very close to each other, then of course this assumption here is not going to be true. And we won't
Okay,
apply
thank
this
you.
to the place when it's not expected to be true. So I want to apply this only in this earlier part in which I see these oscillations.
Do you use this formula to construct initial value problems for numerical relativity? Because I see some.
No, that's an entirely different thing. So I'm
Oh,
going to use this
okay.
in a very different way. So I'll explain that, right? So
Okay.
the thing that I need you to do is to accept that you have this equation for the frequency evolution of a binary system under the assumption that it's losing energy due to gravitational radiation. Okay, so you can derive this from just the assumption that the rate of change of the quadrupole moment tells you how much energy is being lost from the system, and that has to be balanced by the rate at which the energy of the system is changing, and the energy includes the potential and the kinetic energy. So as the energy is being lost, so because this is gravity, so it's unstable, so the thing actually moves faster, and the two objects come closer to each other. So that is the
Okay.
basic sort of ingredient going into this equation. And the
Okay.
strange
Thank you.
powers you see of 11 by 3 and so on, you can think this is coming essentially from Kepler's third law. And Kepler's third law tells you that the square of the period is the cube of the distance of the separation between the two objects. So this means that there's powers of 3 and 2, and this is what leads you to this strange exponents that you see here. Okay, so I'm not going to derive this for you, but just take it for the moment on faith if you wish, or the derivation is not that difficult. We can also do it separately. The important point is that what appears in this equation is this quantity which I'm calling here the script m. So it's a combination of the two masses of in the binary, so M1 and M2, and this is called the chirp mass of the system. So it's the only sort of system parameter that appears into this equation. So if I have two objects of mass M1 and M2, so that gives, from that you can calculate what this script M is, and that determines for you what the rate of change on the frequency is. So, yeah. Okay. So is this part clear? At least
yes, and we had Kostas Kokotas talking about this as well.
Okay, very good. So he talked about how this equation was derived, is that?
Well, he introduced the concept of the chirp mass, and I probably the same equation. Yes, I think all of this is coming from the same approach, which is yeah.
Okay, and of course, as you see from here, that if you just integrate this equation, that's very simple. Then you get that f to the minus 8/3 should depend linearly on the time. And formally speaking, as the question I had before said, at some time the frequency will diverge to infinity. Okay, so that is simply telling you that the assumption under which you derived this was not valid anymore. Obviously, in this actual event, the frequency is completely finite all the way through. It never goes to infinity. It is simply that this approximation is not valid all the way through the system. It's only valid in this early part when you might think that you have two separate objects sort of orbiting each other and then emitting gravitational waves. By this time here, the two objects are very, very close. They merge to form a single object. And this last bit, which is an important part of the second half of the talk, so that is the case when the final black hole is formed and it is sort of settling down to its equilibrium state. Okay, so we will come to that part. It'll be very important later on, but for the moment, the equation that I just said is only valid in this early part of this data. So we get from here that this f to the minus 8/3 must depend linearly on the time, right? So this is a simple integration of that equation. And then from this, in fact, just from this statement here, you can estimate what the chirp mass of the system must be. How do you do that? Well, as I said, you print this data on a big sheet of graph paper if you wish, and simply mark the times between the successive zero crossings. So here, 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 and stop at some point before the peak. So stop somewhere here, because we said the equation is not valid beyond that, right? So we want to stop somewhere around here, and do the same for the Livingston and for the Hanford detector. So then you have the set of points in which you have on the x-axis the time at which you do this zero crossing, take an average of the times between the left and the right end, and you have the frequency that you measure from the separation between them, right? So therefore, it means that you can make a plot of the frequency to the minus 8/3 as a function of the time. So that gives you, in this case, a plot like this. So on this axis is the time, and on this axis is f to the minus 8/3, and it's been scaled to 10 to the 5 just to get sort of numbers to a reasonable scale. Okay. Then you get these points here, and you can fit that to a straight line, right? Because we expect that f to the minus 8/3 has to be proportional to the time. So there has to be a linear relation between them. So let's just fit them to a straight line. And let's find the slope of the line. Again, you don't need to have any fancy calculators for this. You can simply measure this, again, with a paper and pencil and a ruler. And actually, if you do it, it actually works out. So I've actually done it. If you do it carefully enough, you can get the answers that I'm going to tell you about in a minute. Was there a question?
Yes, Badri. Can you, because I was distracted for a second. So you have here this blue.
Yeah, I will explain that in a minute, but I just want to give you the dots at the moment, right?
Yes,
so the
these
dots
are
from this from the data.
From the data. Okay, down to 34 seconds or something like that.
Yeah, 0.34. So this is sort of a reference time. So you just I mean, the scale of this is not important. I mean, the absolute value, the difference in time is important here.
Yeah.
And this is with some reference time, which is zero in that. So it depends on here, right? So it just starts from zero at some sort of early time.
I understand the error balance are growing as you approach as the semi-major axis is decreasing because you have less and less synchronous ratio, or how is that?
Well, this is from the fitting. So I mean, that's a so for the dots themselves, we should not have any error. I mean, there are error bars, but you cannot estimate that directly, right? So first of all, the first thing is before you sort of jump ahead, right? Just make sure that you understand what the dots mean here, right? So that is the actual data.
This is the actual data. Okay.
Okay, so this is what you get from this exercise of printing this on a sheet of paper and measuring the time between zero crossings, and
Okay.
then converting that to a frequency, and then raising that to the power minus 8/3, right?
Okay.
And that gives you each of these points is derived in that way.
Okay.
Okay, and then you want to fit this to a straight line.
Sorry.
Yes, go ahead.
Yes.
Sorry, this question is a bit late, but I was just thinking about it. Why I still don't understand why can you not have a similar gravitational wave event from a very massive star explosion or something like that? This like what is the physical argument for that? Because I've never calculated that, so I don't know the reason.
Yeah, the star would have to be too massive, so that is in a sense the problem here.
So it has to be really okay. And what? So by too massive, what do you mean? Can you give a number on
So we'll
that?
come to that in a minute. So let's just go with
Okay.
this for a moment, right? And then we can see the implication of that, and then we'll see why this could not have been sort of a normal star. Okay, and then you can have an alternative model in which you can think of sort of a very weird massive star. And again, the issue would be that to get these kinds of sort of frequencies in this time, so that is very, very difficult. So you cannot have stars of that size. I mean, no equation of state will support that star, essentially.
All right. Thanks.
Okay. So now let me explain what these lines are. So this line is if you just fit the slope of this a straight line to this data, you see from this equation that the slope should depend only on the chirp mass. So given a value for the chirp mass, that means that you have a slope for this line. Right? So now for different choices for the chirp mass, then you would have, in fact, different slopes. What is shown here are the slopes. The green one is the best fit. The blue one is at 30 solar masses chirp mass, and the red one is at 40 solar masses. And the error bars are coming from this least squares fitting procedure.
Badri, I'm confused. Maybe because I'm not following. But so the chip mass is one of the parameters that you can best extract from the detection, right?
Well, I'm just extracting it I'm telling you the procedure here, right? So the procedure for me to extract the chirp mass is that I have these points, I fit a straight line, and the slope of the straight line from this equation here gives the chirp mass.
Okay, keep on talking. Keep on talking.
So that means that if I change the value for the chirp mass, I get a different slope here. And from a least squares procedure, I can get a best fit value for the chirp mass, and that is shown in this blue and in this green line. And that is a chirp mass between 30 and 40 solar masses. So if you were to make the slope for the blue one, so that is 30 solar masses, and the 41 is the red line. So the green one is sort of the best fit between those two ranges. Okay.
Okay.
And yeah, so let's just for the moment assume that the chirp mass is about 30 solar masses. Okay, just to proceed for the moment. We can get a more accurate value even from this analysis, but let's just assume 30 solar masses. So what does it imply then for the system? So let's assume again, let's simplify life, right? I mean, you can extend this argument for unequal masses, but let's just say that the masses were equal. Then it means that from the chirp mass, you can actually estimate what the total mass should be of the system. So if you go back now here and look at the expression for the chirp mass, so this is this combination of M1, M2 divided by M1 plus M2. Okay. Then set M1 equal to M2 here. So it means that M1 equal to M2, and each of them is equal to 1/2 of the total mass. Okay. So that means that from the chirp mass, you can estimate what the total mass would be for that. Okay. And it's easy to just do it. It's just 2 times 2 to the power 1/5 times the chirp mass. So that is the total mass. So if the chirp mass is about 30 solar masses, the total mass must be about 70 solar masses. Okay.
Yes.
So let's then combine this with what we expect from Kepler's third law. So if the frequency of the orbital frequency is 70 Hz, as we just discussed, so that means that the separation between the two objects, you can just calculate that since you have the frequency, right? And you have the total mass here. You can calculate this, that the separation between the two objects must be about 350 kilometers. So this tells you, this is quite remarkable, right? So this tells you that, in fact, you must have this massive amount of mass, 70 solar masses, has to be confined within 350 kilometers. Otherwise, the two objects would touch each other, and you don't have a binary system anymore.
Okay.
Okay. And in fact, if you then assume that these two objects are Schwarzschild black holes, so then the radii for the mass to be 70 solar masses, each of them is like 35 solar masses, the radii would be about 100 kilometers. So that means that in that case, it would actually work. So in that case, the two objects would then fit into this orbit, and they would not touch each other.
Okay.
Okay, so this is sort of the back of the envelope calculation, if you like. So it's sort of a heuristic argument for why we believe that, why you might believe that the two objects that are merging are in fact black holes.
But it
Otherwise,
is indeed...
you cannot have a star so massive and so compact. So that simply, we have no way in physics of making that work.
But it's indeed heuristic, yes.
Yeah, so this part is heuristic. So this is not a proof, but this is a first argument for why you believe that the signal you see is from a binary black hole. Okay. So any questions on this part? So we'll soon move into sort of more complicated things, but I wanted to be sure that at least from this very simple analysis, you understand why we believe that this signal we see is from a binary black hole.
Yes, are you following, all of you? Costa,
I'm following. It's just that it's a bit too heuristic for my taste.
Yeah. So I mean, as I said, you'll find many complicated analyses in the literature, of course, and there's probably many of those. But the first is you want to know. I mean, the simplest thing that you try, a spherical cow, does it actually work?
Yeah, but that's completely fine. Veronica, Vasu, all of you, Cuba people, are you following, Badri?
I am following.
Yeah, I'm following.
Oh, okay.
Still, yeah, just the question about something else being there was bothering me. That's all.
Okay.
Yeah, so as I said, that if you have a different model, so if you have a model that you have a star that is collapsing, and you can make it work, then you should publish it.
No, I guess you're going to talk about it the next object, but when you have an electromagnetic counterpart, it gets easier to understand the system that you're looking at, maybe.
But I don't want to do that. So
all right.
Yes, it's too dirty. It's too dirty. Yes.
So it's not even dirty, right? So you should understand that in this field, we've been. You saw the results from 2015, but we've been doing this thing for like 15 or 20 years before that. And in that time, we never saw anything. And astronomers would in effect laugh at us, right? You're just observing noise and you're not seeing anything. So very good. Continue and do the best you can.
Not all of them.
Not all of them, yes, but many of them. So in this case, we could see that, well, we found an event, and astronomers, you guys have no chance of finding this in the sky. So these are two black holes merging, and we'll tell you where it is in the sky roughly, and
just for the record, Leo Barak was referring to what Vasu was interested on as astrophysical dirt on the first day. But anyway, keep on talking.
Give me just a minute.
So this is just to get the general idea of what is happening, right?
Sorry, what?
And this is just to get like the general idea of what is happening and how you could, in principle, obtain the mass. I mean, as you said, this is not a proof that this is a black hole.
Yeah, that's going to come now. So, but
Okay.
there's two parts. Right? The first part is a heuristic argument for why you believe that these two objects are black holes, and the second part is going to be the proof that the final object that is formed is in fact a curved black hole. Okay.
Yes, go for it, Badri.
Shall we proceed? Any other questions on this part? Okay, so let's proceed. So now the next thing is going to be the event 1905-21. So this was, as I said, almost exactly 2 years ago, at very early in the morning European time. So in Cuba, this would be sometime in the night at about, 10 o'clock or 11 o'clock. And yeah, so this is data that was published by the LIGO-Virgo collaboration. So you see, first of all, that this data looks quite different in the sense that you see oscillations, of course, but you don't have the long in-spiral part in this event. Okay, so if you compare this to the thing that you saw earlier, this one, you see really this clear chirp signal, right? You see these oscillations increasing in frequency, reaching a maximum, and then leveling off. For this event, it's nothing like that. So you see this blip, which has frequency. This is a time frequency diagram here. At first sight, this has frequency essentially just in the range of 60 hertz, and nothing more. So the previous argument that I said actually wouldn't actually work here, because this is just the in-spiral for this is simply too short. So you could never hope to estimate the total mass based on that argument for this event. Okay, but it is a real astrophysical event. So this was seen in Hanford and Livingston. Virgo had a smaller signal there, but there was the analysis done by the LIGO-Virgo collaboration. They reported that this is actually, from the criteria that we have so far, there's an astrophysical signal, and the false alarm rate is roughly 1 in 28 or 30 years. It means that hypothetically, if the detectors would be running in the same state for that long, you would see one event of this kind. So it is a significant event, and it is an astrophysical event. And the question is, what is it? Is it a binary black hole? And in fact, can you show that this final object that is formed here is in fact a black hole? So before I proceed to the analysis of this event, I just want to make one point, which is that if this is a binary black hole, then it must be a very, very massive, even more massive than the first event that I just discussed, right? The first event was about 70 solar masses, as we just saw. This one would have to be even more massive. So why is that? Well, let me just give you an example here from 3 events that were seen by LIGO back in 2015. Okay. So 3 events. That was the first event was we saw these few oscillations and then the merger. There was one more event which happened in October of the same year. So that was a longer event. So we saw many more oscillations in that event, and then a merger, and then the last part. And there was an even longer event, which was 15, 12, 26, which had a very, very long in spiral and a merger and a ring down. So you should keep in mind that for any of these systems, even for the heaviest ones, they've been orbiting each other for millions of years, and we just see the last part of this event. Okay. It is simply that the LIGO detectors have a frequency bandwidth, which is it has a sensitive bandwidth, right? It cannot see something below, in that time was about 40 hertz. So any signal below 40 hertz you could not see. So it means that that signal is visible in LIGO only once its frequency gets above 40 hertz. And this happens for and this depends upon the mass of the system. So for these events, since it's just pure vacuum with just 2 black holes orbiting each other, the only time scale is set by the total mass of the system. So that means also the frequency of the event, the typical frequency scale, is set by the mass of the system. So it means that for very massive systems, those have a much lower frequency. So that means that for 5914, so this plot on the left is just the same data in the frequency domain. So you take its Fourier transform and you plot that on the frequency versus amplitude versus frequency, you'll get a plot like this. So this is then, in effect, the inspiral phase. It just has many orbits here at low frequency, so the amplitude is larger, but it's decreasing in amplitude. This blip that you see is the merger in the frequency domain. And as the system becomes more massive, this whole thing moves to the left in this graph. So that's why the blue event, which is the most massive one, is most to the left here. If you imagine a more massive system, the whole thing will move even further to the left. So just at the very edge of this sensitive bandwidth here. And then you would see just the very last part of the signal. Okay? And so that is what is happening here. So in this case, you see the very end of the merger. So which means it's a very massive system so that you do not see in LIGO the earlier part of the event. Okay, is this point first of all clear?
I think so.
Yes.
Okay, very good. So now let's see. So in this case, we have no hope of getting any information from the inspiral, so that we just saw. But we have the merger and the ring down. What are these things? So the idea is that when I have these two black holes that orbit each other, they form the final black hole at some point. When this final black hole is initially formed, it's quite perturbed, right? It's not a simple equilibrium state. So it's time dependent, and like any object, then it approaches equilibrium. So think of then a system like a bell, right? You strike a bell, it rings, and it reaches equilibrium in the end. So the same thing happens here. This final black hole, once it is formed, it is distorted, it is time dependent, and then it loses all of this deformations by emitting gravitational radiation. The technical details are more complicated, but this is sort of a heuristic way to think about the whole process. So it means that at some point, once this black hole is close to its equilibrium state, so let's now say that this equilibrium state should be some final state, which is a stationary solution to Einstein's equation, which we will assume is a curved black hole, in fact. Then what it means is that at some point, you should be able to explain the full spacetime as a perturbation of this curved spacetime. Okay? So I'm not going to again explain the details of this calculation here, but what I need you to sort of again accept in this case is that in GR, if you have a curved black hole, so it means that you can actually calculate how this black hole approaches equilibrium. In other words, the black hole emits these quasi-normal modes. It means that it has damped oscillations at the very end. Same thing happens for a bell, right? If you strike a bell, you hear a tone, the frequency of the sound, and the sound amplitude then decreases in time. Okay. So there again, you have a frequency and you have a damping time, and you have that for any star and for any physical system. So in this case, for black holes, for a curved black hole, you can actually calculate what these frequency and the damping times should be. Okay, based on a purely theoretical calculation, you can calculate at what rate this amplitude must decay in time and what the frequencies of these oscillations must be. Okay. Has anybody discussed this in any of the previous talks?
Yes, actually, we had Alejandro talking, but well, he hand waved his way. He gave a hand waving presentation of this without any mathematical equations, etc.
Good. I'm also going to wave my hand even more, and I'm also not going to have any equations. But the only thing I want you to take from this is that you have this prediction in GR that you have this infinite set of complex frequencies. Complex, why it's got a real and imaginary part. The real part is the oscillation frequency, and the imaginary part is the damping rate. Okay. So you have this infinite set of frequencies determined by three integers. The three integers are n, l, and m. So the L and the M are the usual angular contour numbers, right? So it depends on what mode of perturbation that you're doing. And this L and M are the angular contour numbers. And this N is the overtone index. So this in quantum mechanical is number of zeros for the radial wave function, if you wish. Okay. So regardless of that, I mean, GR predicts for you this infinite set of frequencies and damping times for a curved black hole. Now, the remarkable thing is that because of, again, Monica has again done my work for me, so according to this black hole no-hair theorem, this infinite set of numbers should depend only on two quantities, which is the mass and the angular momentum. Okay? So that means that, yes.
Sorry, I have a question. Are the Kerr black holes stable under this perturbation? Could we have something of a resonance or something that could break the validity of these equations?
So this is in fact part of the proof that the Kerr black hole is stable. So a full proof that it is stable is there for a Schwarzschild black hole. It's a mathematical proof. For a Kerr black hole, I think it will get there, but at the moment for slowly spinning Kerr black holes, you can do it. But there's all the numerical calculations and all other kinds of evidence, which is not, mathematicians will not say it's a rigorous calculation, but still, the Kerr black holes are stable, and this is how they approach equilibrium. So this is, if you wish, a result from GR.
Okay, thank you.
Okay, so nobody's found a way to break a Kerr black hole classically, if you will. And this is a very strong prediction, right? So you get this infinite set of frequency mapping times determined just by two numbers. And this is, in fact, the thing that distinguishes a Kerr black hole from other, or a black hole in GR from other objects, like a bell, right? So if I take a bell and I want, and for that, of course, you can also calculate what its allowed frequencies and damping time should be. So these are the quasi-normal modes for a bell. So you'll find that that depends upon the shape of the bell on very complicated things connected to the bell. And same thing for a neutron star, if you were to do this. I mean, you would find, again, these frequency and damping times, but they're much more complex for these systems than it is for a Kerr black hole. For a Kerr black hole, again, everything depends just on these two numbers, which is the mass and the angular momentum of this Kerr black hole. Okay, is that point clear? So this is a very non-trivial calculation coming from GR, which restricts that this infinite set of numbers should be determined just by these two quantities.
Yes, thank you.
Okay. And this is what, in fact, we're going to use to prove this that this is a Kerr black hole. It's now the assumption. It's not an assumption. It's a very, very special relation that this frequency damping time should be determined just by these two quantities. So now it's a little problem, right? So now let's say that you just find one frequency and one damping time. So you just find one value, one complex number omega. And you don't know which mode it is. You don't know what the values for n, l, and m are. For each, so again, each of these complex numbers should depend just on the mass and the angular momentum. But unless you know what the n, l, and m are, you cannot actually calculate what the mass and the angular momentum are corresponding to that frequency. Right? So then the procedure that we have, which is called now black hole spectroscopy, is that you do the following. You make every possible choice of n, l, and m for every observed frequency and damping time that you have. For one choice of this NLM, you will get one result for the mass and the spin. And you repeat this for all the modes that you see. So there must be then a consistent choice of the mass and the spin and a choice of these mode indices such that everything agrees. So that is then your proof that what you're seeing is a Kerr black hole. But this also means that this cannot work with just one mode. You need two modes. If you just have one NLNM that you observe, then of course what you find is a mass and a spin. So you could always find a mass and a spin consistent with that, right? So to actually do the check, you need at least two of these modes to be observed. Okay, is that point? That's the key point here. So is that clear? So with just one of these quasi-normal modes, you cannot prove that there's a Kerr black hole. You can find consistency for different choices of this n, l, and m, but you cannot prove that this is a curved black hole. To do that, you need at least two modes.
Is this clear, people? Do you want Badri to go through it again, very briefly?
I think it's clear enough, although I do not trust myself to do work with just this. I mean, these are mathematics. We should sit down and study.
No.
Well, it's not really. I think that the talk is very simple, right? So it's simply that you have this is a complex number, so you have two real numbers in it for each NLM, right? And then you have
Yes.
the mass and the spin. Those are again two quantities, right?
Yes.
So given the mass and the spin, or given again the real and imaginary part of this complex number, you can find the mass and the spin, right?
Okay. Yeah. Okay. It's
But
clear enough
again,
now.
it depends upon what these indices are. For each choice, you will find a mass and a spin. And this is not
Yes.
true only if you have two of these complex numbers, then you have two independent measurements of the mass and the spin. So there must be a consistent set of mode indices, which makes it consistent, right, of the mass and the spin. So that is the
Okay. I think I understand now.
So now let's do that. So now this is then the result of our analysis, which we on the archive just a few days ago. So this is the result. So let me just go through this very, very slowly, okay? Ignore the right part entirely that is the important part, but ignore it completely for the moment. I just want to focus on this left panels here, okay? So so this is a distribution function, a probability distribution for the damping time and the frequency as from this event, right? So we take this event here that is seen here, and we try to fit this with these damped sinusoids, which are coming from this calculation that I just said, and we choose different starting times to do this fitting. Okay, you choose a time here, assume that it's a damped sinusoid to fit that to the data here. You a little bit more to the right, a few milliseconds, repeat the same thing, and at each time you can get by the fitting procedure a distribution function for the frequency and the damping time for the system. So it's very similar to this time frequency plot that was shown by Ligo, right? So again, here is your frequency around 60 hertz at a particular time in this, of course, and we see the same thing here. So it's around 60 hertz, and this is the frequency axis, and that is the damping time axis. So we see excess power at about 60 hertz, and the damping time is about, what is it, 0.02 something seconds. Okay, and this contour here is a 90% probability region. So with 90% probability, the frequency and damping time should be within this contour. So this analysis you cannot do on paper and pencil. This actually needs serious computing, but still, it's not a complicated thing to explain, right? I mean, at least the basic is clear, is that you try to fit the data with these damped sinusoids, and then you want to estimate what the frequency and damping time for this signal are. And if you look at along the frequency range, you see this distribution for the frequency. Okay, and then again, the shaded region in this plot here tells you the 90% interval for the frequency. Right. So now what is done is the following, and so what we expect is a dominant mode of the gravitational wave is the L equal to M equal to 2 mode. I mean, you can make a different assumption, but again, you will always end up on this, the result I'm going to explain now. So let's say that this is the L equal to M equal to 2 mode. So in other words, if I go back here, so omega 0 to 2, so that is the mode that we find in this frequency range. Okay, and this contour tells you the 90% probability of the frequency and damping time. So by assuming that this is the L equal to M equal to 2 mode, you can in fact calculate what the mass and the spin should be. So that means that you can actually calculate what the other modes must be, right? So this 90% region, you can translate that to what the other modes must be. So this shaded, the purple region here, is the expected 330 mode. This is the expected 440 mode, the expected 550 mode, and you can have all the infinite set of modes. We're just showing 3 here, which are among the relevant ones. But you have you can predict from this first calculation here what all the modes must be. And the width of this corresponds to the width of this gray region. Okay, just translating that to what the other modes must be. All right. And then you can do a more detailed analysis of this frequency range. And in fact, we find, amazingly, very strong support of something consistent entirely with the 330 mode, as predicted by the Kerr black hole, for a Kerr black hole. So this part, this second panel here, this is not evident if you just look at the data here, right? Hidden in this is this high frequency component, which you cannot find just by looking at it. You need more complicated analysis, but again, it's easy to explain what is done, right? And this is the distribution function for the frequency and the damping time for this second mode. And is entirely consistent with the Kerr black hole.
Badri, what was the synchronous ratio of the source?
Right, so that's, in this case, it is about 15. So roughly speaking, for this first event, this SNR is about 10 or 11, and this is about 4 or 5 for the second one. So it's a weaker signal. It's not something that is entirely trivial to extract. In fact, you can say the LIGO, they missed it, so they only provided evidence for this one. And in fact, they did not report a result for this second one.
I just wanted to repeat maybe what you said. So 330 here just means L equal to 3, M equal to 3, and N 0, right? That's
exactly. That's what this indices mean exactly. So okay. 0 stands for the overtone index.
All right.
3 is for the angular modes. Yeah.
Okay, just wanted to confirm. Thanks.
Exactly. Okay, so this is sort of, we'll sort of expand on this in the next couple of slides, but this is sort of the proof that this is a Kerr black hole. It's visually completely obvious in this plot. Okay, so any questions about this?
So the right panel is based on information that you have from the left panel, right?
Well, what is based on the right panel from the left are these the shaded regions, sorry. This region, and this. This is obtained from the left panel.
Mm-hmm.
Everything else is from the independent calculation of the data. Of course, these contours are also. So these dashed lines are from the left panel, translated from information from this contour, translated to here, to these other modes.
And what are those big contours where you have?
So that is from the data. Yeah, sorry. So this is from the actual data. Okay. So as I said, from this calculation, we get the distribution function for the frequency and the damping time. So these contours are this is the 50% contour, this is the 90% contour, so this dashed line here. Okay. So within 90%, of course, that would be all, but this is, this is again, I'll expand on in a minute, but this is sort of the fact that the distribution function is peaked exactly where the prediction is. So that is the proof that this is a Kerr black hole.
And why does the 90% contour have that weird feature on the right?
Yeah, so this is always the PSO distribution, always harder to sort of explain. So okay. If this had been an even louder signal, if this had been not SNR 4 or 5, but SNR 10 for the subdominant mode, that would be much more concentrated, right? So the fact that these features you see, this would go away for a louder event.
Okay, thank you.
Okay.
And Badri, since you are so modest, how many people did this work? How large was a group of people involved in this work?
Well, you can look at the author list, 8 people on the author list.
So 8 people as compared to 1,000 in the LIGO collaboration?
Exactly. So that is an important point, yes.
Mm-hmm.
Can I ask something? Hello, Badri.
Yes, of course.
It's actually a follow-up from what Pau told. Why didn't they do it? Because essentially everybody knows about the quasi-nova modes. Everybody knows about parameter estimation. They had the data before you, so why didn't they bother?
That is a good question, right? So
Just for the record, Stamatis is Badri's student, so he's just trying to make him smile and make him feel comfy.
Yeah. So, well, we're pretty proud of this, right? So I think the point is that, again, it goes back to this heavy, I mean, there's many smart people in collaboration. There's nothing against them, of course. So, and I think the reason they missed this is not fully clear to me, but an important part of this is that this event is not doesn't have an in-spiral portion at all. So what it does have is the merger and the ring down. And the usual way of this analysis is that you take these waveform models, which include both the in-spiral, the merger, and the ring down, and you try to use that to extract information from the system. And because of the lack of the in-spiral part of that, so that analysis has more errors, let's say, it's more uncertain. And so therefore, that analysis predicted a value for the merger time, which happened to be somewhere here. So in all of the ring analysis, at least the one that is published, they started a bit later than we did. So they started the ring down analysis a bit later. That means that by that time they started it, the second mode had already disappeared. So that's why they didn't find the second mode there. So now it's a different question. Why? Now you can say, well, that seems like a trivial thing. They could just have also started earlier. And in fact, some people in the collaboration did also this analysis where they started earlier. So that I'm not sure why they missed that. So that I think is something that the collaboration should discuss.
Okay, Badri. So, but this is very big news, right? It's not news for you because the paper has been out for a while, but this is a very, very strong evidence that this object was indeed a black hole and nothing else, like a gravastar.
Exactly. So this to me is the closest that you can get to a proof with the present data. And this is very promising that in future events, when you have louder signals, that the error bars will become even smaller, right? So then you should really be completely consistent with the prediction.
Because just to let the younger people know, when the first discovery was announced, I asked the question: do you have an evidence that this was a black hole? I was in a room full with 25 people doing data analysis. I'm not going to say names, but all of them were quite convinced that this was a black hole, and I was not. And we did some short calculations at Blackboard, and I managed to actually convince them that they did not have proof of that. And then Bernard Schutz came to visit, and he explained that somebody had claimed that that discovery would lead to two different Nobel Prizes, one for the discovery of gravitational waves, and a different one for the discovery of black holes. And he said that he had told this guy this was wrong.
Yeah.
So these are very important and nice results. Congratulations.
Yeah. So this is again some more. Let me just show you this result here, right? So now let me just explain to you what this is. So what we do is now a test of the no-here theorem, which is that is it really the case that we just have the two parameters describing these two complex frequencies, right? So what we do is the following. We said, well, let us now relax our assumption. Let us not assume that the second frequency here is exactly as given by the Kerr prediction. So let's introduce some deviation parameters. So let's assume that this is the 2-2 mode. And let's assume that for a 3-3 mode, the frequency and damping time are a little bit away from Kerr. Let's include that assumption now. So now we no longer assume exactly that it is Kerr, but we allow for deviations from it, right? And the question is, how big are the deviations, and how can you constrain them? So that is then this result here. So what is done here is that you say that, well, we have possibly some fractional differences allowed for the 330 damping time and for 330 frequency. And let's try to estimate what these deviations could be, right? So it's now an extension of the analysis that I just presented, right? So there I said that everything should be Kerr, and now here I'm saying that, well, let's allow for some deviations. And what you find here is this is then the result. So again, the green lines are the curve prediction. So that is then exactly, if everything exactly is at the intersection of the green lines, that is exactly curve. And this is then easily within 50%. It is curve. I mean, so the confidence is of, let's say you can measure it in this way. You can say that delta F330, the estimated value is this number plus or minus these error bars, right? So this is 10% roughly. So it is 0.012 plus or minus, it's a fraction, so it's plus or minus 10% plus 7% minus 10%. So you can say that within that error bar, you're then confirming that this frequency is as predicted by the Noether theorem. In other words, within 10%, you're confirming that the black hole exactly is a curved black hole. For the damping time, it is much less certain, right? So it is a much larger error bar. So the frequency is the thing that really distinguishes it. So again, the frequency is much better constrained than the damping time. So that's why we say that, well, we confirm the Noether theorem to plus or minus 10% in this case. Okay. So there's more thing with overtones. I'm not going to get into that. So I'm just going to stop here. So I hope I've convinced you that LIGO really does observe black holes. But now the thing is that, well, it's again the question of confidence, right? So of course the error bars we've reduced it, but you can use it even further. And at some point, the hope is that you can find smaller deviations. You can start playing with sort of the boundary conditions in how you calculate these cosinoval modes. You can include quantum effects and some small deviations. But at least now we really believe these are curved black holes, at least at this level. And really to go into the details, there'll be smaller deviations. And now we can start looking for them with this and with future events.
Can I ask something?
Yes, so but I'm done with the talk. Yes, of course, you can ask.
Okay. So in your opinion, which models are completely out of question given this result, and which have like some space within error bars?
Oh, you mean what thing does this rule out among the alternative GR?
I'm guessing that somebody is asking if with these results, and the answer is yes. For instance, wormholes and
yeah, so this particular event has sort of led to maybe 30 to 40 papers within 1 year with suggestions of what it could be. And yeah, so there's a different suggestions. I think we rule out many of them. So at least things like, a black hole with a massive disk around it are ruled out. There's things about a Procastar mergers. I think that is disfavored now. So that will be more of a study, but I think it does rule out many of those things in the literature.
What about these UCO, so extreme compact objects, which they assume kind of equation states?
Yeah, so I think those would have a different ring down spectrum, I think. So yeah, so I think, yeah, I'm not sure. I haven't done the comparison there, but I think you could constrain those models as well.
I see. Okay, thanks.
What are those models, Stamati? I didn't understand.
I mean, Planck stars or boson stars. So it's the same thing. So it's not GR. You assume something and you can make it shrink to whatever radius you want. So you can play with compactness, and they all kind of mimic black holes. So I was wondering.
Yeah, so for Grava stars and boson stars, if you have the cosinoval mode calculations for them, then you can actually start to compare.
I see.
But we haven't done that yet, so I think that's an interesting thing one could try.
So basically this is very nice because now I can appreciate that we actually have seen a curved black hole. So this is, I cannot recall the mass. Can you remind me what mass is?
I cannot recall because I didn't show it.
Okay.
So the thing is that's a tricky question because of course LIGO Virgo, they reported a particular value for the mass, but that was not based on analysis like this. That was based on the full waveform analysis. Okay.
All right.
And the point is that is not reliable. So, but what you can do is you can, from this frequency band, you can estimate not the source mass, but the redshifted mass that we see at the detector.
Right.
So that is if you 1 plus the redshift times the actual total mass.
Okay.
And that is something around 320 solar masses in this case.
Oh, so that is massive.
That is much more massive, yes.
And what was the mass that LIGO was reporting? So I just want to know how much is the disparity?
A factor of 2, basically. So that's
All right.
150. But there were other results. So again, it's a very complicated analysis with this complete waveform models, and there's the distribution function has many local maxima there.
All right.
So there's a reanalysis of that, which led to a different mass ratio and a different total mass. So it's a difficult question.
All
But at
right.
least from the ring down perspective, what we see is a redshifted mass of 320 solar masses.
So then you can expect with maybe LISA, you can have better analysis and you can do the same testing for different sources to sort of have a nicer statistics over
Exactly.
this. Okay.
And even with I think future, we published a paper just last year or something that this could not be possible based on population models that we have for how massive the black holes would be and what the mass ratios of the binaries would be. So from that you can estimate how loud the second ring down mode should be.
All
And
right.
the prediction was that with LIGO would not able to find it, and you would have to wait for like ET or at least for the next 10 or 15 years, but not before that. And we disproved ourselves in this.
I have one last question, and this is a bit more technical. I think so. It's just a bit. I was just curious. LIGO has a huge list of catalogs, right? So how do you pick the sources that would be of interest? This is something I probably people understand this, but I don't. How do you choose the right candidate that you end up having, or did you do a multiple analysis on different kind of data sets and then you found this to be the best indicating?
Well, in this case, this particular event is very heavy. So this is the heaviest event so far.
All right. Okay.
Even with the estimate that LIGO Virgo had. So that alone picks it up, right? So it's got a very small in spiral, and it's the merger and the ring down. So you can imagine that any effects of the merger and ring down should be dominant here.
Okay. All right. Okay.
And there's one more reason, which is that there was some analysis, a very nice analysis by Alex Nitz and Colin Capanos, who are also authors on this paper. So they had a reanalysis of the event before this, and they found that they could fit a different mass ratio to the system than what LIGO Virgo reported.
Okay.
And so that is what led us sort of to this event. And Colin has done the bulk of the work here, I can definitely say that. So that is what led him to this particular event in particular.
All right. And should there have been a multi-messenger counterpart to this?
No, the binary black holes, right? So I don't think.
All right. Sorry. Okay. But even not even from any kind of accretion, that means.
Yeah, so in the paper before this, right? So this reanalysis of this event, so they did sort of attempt to make an connection to an event seen by the Zwicky transient factory.
Yeah.
But I think it was inconclusive. So I think.
All right. I would have guessed it's difficult. You would probably not have something, but I was just curious if from accretion you see something. All right. Thank you.
So anyway, the catalogs of LIGO are not that large, and their public data is a subset of that. So it's not a big deal.
Yeah, no, I just thought because I can see that this is a lot of work. So I was just curious how
Let's say that more than a lot of work, this is a smart work.
Yes, that's true. And a very smart work. That's why my question was, how do you smartly choose the right? But I didn't realize that this was actually one of the most interesting sources there already.
But for the part about population synthesis that you mentioned, Badri, why do you do that?
Why did we do that?
Yes. Why did you're shooting yourself into the foot? You don't do that.
Well, the benefit is that in doing that, you need to develop the analysis methods for doing this analysis as well, right? So
yes, but you see what happened. You see what happened?
Yeah, it's true.
Anyway,
not just us, right? Nobody expected this. So all the they're not just us. other papers also said that you will not be able to see a second mode based on the population that we expect.
Yeah, you don't expect anything because they have like 15 free parameters. Anyway, do you have more questions for Badri?
I have another question. Do you have an explanation why a conceptual maybe why is it so different? Because in the full in spiral merger ring down waveforms, you do have this information from the ring downs, from the quasi-normal modes. Why was it so wrong? Since
But
the information was there.
It is, in principle, it should be there, but I would say that the again.
Sorry, I lost the connection and I couldn't hear the question. Could you repeat it, please?
So the question was that Stamatis said that this IMR waveform, the waveform which model the in-spiral merge and ring down, I mean, they do model the ring down, right? R is the ring down in those waveforms. So in principle, the ring down there should contain these same frequencies as well. So I don't have a conclusive answer on that. So it's except to say that the way that many of those models treat the ring down is somewhat ad hoc. And also they have to do a job of, for each of these modes, they have to match the in spiral to this ring down. It's a very, very different kind of signals. And in doing this, sort of, if you don't do it exactly right, then you probably lose this information in that.
I see.
So I would say that the short answer is that if, ideally speaking, if you would do the modeling extremely well, then indeed, yes, the IMR waveform should have this information, and you should be able to do this with the IMR waveforms. But I think that points to sort of something that could be improved in those models.
Okay, thanks. So this so this is an update for the mass for the so they claimed that it was the first intermediate mass black hole, and it was around 150. So it's actually 330.
Well, it's redshifted, right? So again, depends on the redshift to the source, and the sort of the thing is that for a binary, it's a standard kind, right? You know the distance, and you can make the link to the amplitude and the distance. From the ring down, you can't do that. So estimating the redshift is not an easy thing with the ring down. You need more information than if you assume the standard thing, then I forget now what the estimate would be. But again, I'm saying that from the ring down analysis, it's not so clear what the redshift should be.
Okay.
Okay. If you have any other question, this is time to ask it.
I have one more.
Go for it.
I was just curious, how else can you resolve this problem of redshift? Or I guess I've heard Samatas also talking about like source localization. So how else can you solve this issue in order to know actual mass and not the redshifted one?
Yeah, so in this case, if you had a detector which was more sensitive at lower frequencies, then that would give you sort of some extra bit of the signal, and from that you could estimate the redshift. So that is something definitely that the future detectors will be able to do for the same kind of event.
Okay.
Okay. Any more questions? I have a lot of things to say, but I guess I should read the paper first and then ask the questions.
Yeah, just emails. If any questions, just send me an email.
Yes, this is the usual thing that they say, yes. But don't expect an answer because battery takes on average 3 months.
I promise if you ask a question about the paper, I'll respond.
Yes. Okay. So in any case, battery, thanks, because this was very nice. And you know that I speak up my mind. And yeah, Yoru, you can stop